This video is on the quadratic formula. This is the most powerful technique for solving quadratic equations. It literally will not fail you anytime. It will work on everything. So it's sort of the brute force technique for solving quadratic equations. And it looks like a challenging formula, but when you know how to use it and you know how to break it up in steps, it works pretty smoothly. Just to understand where this comes from, the quadratic formula is the result of the completing the square algorithm. If you take this equation, the ax squared plus bx plus c equals 0, and complete the square on it, you actually get this equation, or this formula. So I'm not going to go through that. It takes a long time to do. But what we're going to do is learn how to use this formula in this video. So before we start, I want you to memorize something. We're going to memorize what's called the discriminant. This is the b squared minus 4ac. The discriminant is the most important part of using the quadratic formula. Look at it as a formula, b squared minus 4ac. It's going to predict the nature of the roots in our equations when we're solving them. So it's a nice tool for doing that. Another way you can use the discriminant is actually decide if a polynomial is going to factor easily. And we can use that tool there as well. So that's going to be the focus for our approach here using the quadratic formula. So let's get into an example. Okay, so we have 3x squared plus 11x equals 4. So we're going to find the value of x, or values of x. Actually, the exponent of 2 is a reminder for us that there's going to be 2 roots to the equation, or at least 2 roots. It is possible to get what's called the repeated root case. And the discriminant will actually tell you that that's going to happen. So that's what we need to do, is we need to be able to calculate the discriminant first, the b squared minus 4ac. However, the equation is not in standard form. If you look at the quadratic formula, you'll notice that we have to have the equation looking like this. Some number times x squared plus some number times x plus a number equals 0. So this is called standard form for a quadratic equation. So that's what we need to do. We need to put this in standard form. And then we can identify the parameters a, b, and c and calculate the discriminant, and then eventually find the roots to the equation. Okay, so here we go. Let's go ahead and move that 4 so we can get 0 on one side of the equation. Let me write the equation down first. So we have 3x squared plus 11x equals 4. Now, to get this in standard form, we need to have 0 on one side of the equation. So I'm going to go ahead and actually add a negative 4 to both sides of the equation. Notice how I said that. I'm adding a negative 4. I'm thinking in terms of inverses. And I used the sum line to remind me of that. Okay, so we'll add these things. We get 3x squared plus 11x minus 4 equals 0. So now our equation is in standard form. Now we can identify the parameters a, b, and c. So with standard form, remember a is in front of the squared part. So a is going to be 3. B is the linear coefficient, or the number in front of x, just a plain x without an exponent. So b is 11, and then c is a negative 4. Okay, so let's calculate the discriminant. Remember the thing I told you to memorize, the b squared minus 4ac. We're going to start with calculating this thing, the discriminant. Okay, so b squared minus 4ac, we're going to replace b with, we actually know b is 11, and a is 3, and we're going to replace c with a negative 4, and then we just use the order of operations to figure out what this is. So 11 squared is 121. We got to be careful with the signs on this. We're going to do the 4 times the 3. 4 times 3 is 12. So negative 4 times 3 is a negative 12. And this is negative 12 times a negative 4. So actually, all of the negative signs cancel out. We can pair up the negative factors here. You know, this negative sign is from the formula, the discriminant itself. When we pair it up with the value of c, then we get a positive result. So 4 times 3 is 12, and 12 times 4 is 48. So this is plus 48. So now we add these together, and we get 169. So we have the discriminant now. So the discriminant is 169. And if you're familiar with your perfect squares, you'll note that 169 is a square. It's actually the square of 13. So we're going to get two rational roots. Whenever the discriminant gives you a perfect square, we're definitely going to get two rational roots. In other words, the answers aren't going to require us to use the radical notation or the square root symbol. So we're ready now to calculate our roots. So I'm going to actually run the formula. So the formula is here, and I highly recommend you have this at your side when you're doing this. So we're going to go ahead and run that. So what we have then is x equals a negative of b. I'll put a place for doing the substitution. Plus or minus the square root of, that was the b squared minus 4ac. That's going to be the discriminant right here. And then we're going to divide the whole thing by 2 times a. And then now we can just put those values in. So now I have the formula essentially laid out. A negative of b means a negative of the 11. And the discriminant we worked hard to get already. It's 169. And then a is 3. And now we just do what we can to simplify this. So here we have x is equal to a negative 11 plus or minus the square root of 169 is 13 all over 6. So that represents the two roots to our equation. So we can go ahead and now calculate those separately. At this point, we have no choice but to apply the plus or minus to get our two roots. So we're going to jump down here. X equals a negative 11 minus 13 over 6. So we'll figure out what that is. Negative 11 minus 13 is a negative 24. So this is a negative 24 over 6. And 24 divided by 6 is 4. So this is a negative 4. So one of our roots is a negative 4. The other root is x is equal to a negative 11 plus 13 over 6. And a negative 11 plus 13, that's going to produce 2. So we get 2 over 6, and that simplifies to 1/3. And there's the two rational roots predicted by the discriminant, by the b squared minus 4ac. So if we want to, we could actually present these as a list using set roster notation. So x is equal to a negative 4 and 1/3. We always write the roots in order in the set notation. Okay, let's do another example. So this one will have an interesting result in terms of the discriminant. It'll be a different case of the discriminant. Okay, so notice the equation is not using the variable x. The variable is not really that important. We can use any letter that we want to in our equations. We don't have to be locked into just x. Sometimes we might want to get out of the habit of doing that. There's a lot of other variables to use. Use a very common variable in algebra, so we're going to go ahead and use it. So if u squared equals a negative 9 minus 6u, that absolutely does not fit standard form. Standard form for a quadratic equation has to have 0 on one side of the equation and basically everything else on the other side. So we need to move things around. We also need to remember that the variable is not x, it's going to be u. But all we got to do is just change the x to the u in our formula and we're good to go. Okay, so in order to do this, we have to manipulate a bit. I'm going to just rewrite the problem here and start working on it. And actually, I didn't leave myself a lot of room to make this happen, but it's okay. We're going to go ahead and actually add the 9. And while we're at it, we might as well add the 6u because we've got to get rid of both of those. We need to get those to the other side of the equation. So we're going to have a plus 9 and a plus 6u on the other side. And I'm going to use the sum line since I'm using the additive inverse. So here we go. I need to shift things over a little bit, but we're going to get u squared plus 6u plus 9 equals 0. Now I need to write the terms in that order based on standard form for a quadratic equation. We essentially, in polynomial notation, we write the monomials that make up the polynomial so that the exponents on the variable are in descending order. So we got 2, and then u to the first, so 2, 1, and then this is 9u to the 0th, or this is the 0th term, or the degree of 0th term in our polynomial. Okay, so if you're really good at factoring, you recognize that you can actually solve this using the zero product property and factoring. But we're focusing on the quadratic formula, so we're going to calculate the discriminant, which means we need the parameters a, b, and c. So a is the leading coefficient in front of the squared part. So in this case, there's a 1. This is 1u squared. And then in front of the linear part is 6, so b is 6. And then c is 9. And then now we go to work calculating the discriminant. So that's going to be the b squared minus 4ac. And I created a template for doing all the substitutions that we need to do. So b goes in first, so 6. And then a is 1, and c is 9. And then just apply the order of operations to this to figure out what it is. So we have 36, 6 squared is 36, minus, actually 4 times 1 is 4, and 4 times 9 is 36. We get 0 for the discriminant. So this is what we'd call the repeated root case, or the single root case. The discriminant came up to be 0, so therefore we're going to get one rational root. That is a consequence of the discriminant being 0. We're going to get one rational root. And it also makes running the quadratic formula a lot easier. So again, we want to go back and refer to the formula as we do our work. This is going to be changed to a u. So u equals all of this. So we'll run that formula now. So u equals a negative of b plus or minus the square root of the discriminant all over 2 times a. So this can get to a routine like this for you. Create this template, do the substitution. That's the whole point of an algorithm, is to give you something that you can repeat accurately every time. So anyway, it's a negative of b, so a negative of the 6 plus or minus, well, the discriminant came out to be 0, right? And then 2 times a, that's 2 times 1. And then we just figure out what this is. So u is equal to a negative 6. The square root of 0 is 0. So we get plus or minus 0 all over 2. So therefore u is equal to a negative 6 over 2. Plus or minus 0 is just 0 in each case. So therefore that's why we get our single root. So we do have what's called a singleton in this example. So u is equal to a negative 3. Sometimes you might say u is equal to a negative 3 or u is equal to a negative 3, and making a reference to the factored version of this. U squared plus 6u plus 9 is actually a perfect square trinomial, so therefore it's a square of a binomial, and that's another reason why we end up expecting only one root, or what we call the repeated root case. So the zeros to this function, if you thought of it as a function that you can make a graph of, are going to be at a negative 3 on the x-axis. Okay, so here we go with another example. So, let's go ahead and write this in list form. And it is a singleton, so sometimes we can still use set roster notation to write it like that. And, we kind of went out of the way to use set notation here, but I just wanted to demonstrate that even though you have a single root, you can still use the set roster notation. We just call that a singleton. All right, one last example for this video for the quadratic formula. This one is going to involve radicals in the answer, and the discriminant is going to tell us that. Okay, so we'll start by writing the equation all over again. So we got 3x squared plus 12x plus 12 equals 33. Okay, so we need to get this in standard form, which means 0 needs to be on one side of the equation. So we need to actually move that 33. or we're going to go ahead and add a negative 33 to both sides of the equation. And since I'm using the additive inverse, I'll put a sum line in there. These cancel out. There's our 0. We needed that to happen. And so we're left with 3x squared plus 12x minus 21. Now at this stage, you potentially could try to solve this by factoring. The other thing I'm noticing is actually the 3 and the 12 and the 21 are all multiples of 3. So if we wanted to, we can factor out the 3 and divide it out, in essence reducing this polynomial. We don't have to do that. Everything will still work out in the end. But sometimes it helps to do that because, well, if we do that, then a would become 1. And when we run the quadratic formula, it's actually easier. So let's go ahead and give that a try. Let's go ahead and factor out the 3. So we're going to be left with the quantity x squared plus 4x minus 7 equals 0. So we can multiply by 1/3. It's kind of convenient to divide. But notice on the other side of the equation, since you have 0 in there, that just stays 0. So that's actually convenient. And then we can cancel out those 3's. So we're left with x squared plus 4x minus 7. And now we're ready to run the discriminant. So let's calculate the discriminant. Note that a is 1, b is 4, and c is a negative 7. So we'll calculate the b squared minus 4ac. So put everything in position, and then we go to work on this. So 4 squared is 16, and then this will be a plus because the negative sign on the 4 will cancel with the negative sign on the 7. And that's going to be 4 times 7, which is 28. And then we'll combine those. So let's see, we got 28 plus 10 is 38, plus 6 more, it's 44. So we get 44 here. Okay, so the discriminant is 44. And so now we can go ahead and start to simplify the radical by running the quadratic formula. We are ready for the formula now. So the variable is x, so we just go straight to the formula. X is equal to a negative of b plus or minus the square root of the discriminant all over 2 times a. So when we reduce the equation, b ended up being 4, and the discriminant is 44, and then the bottom we have 2 times 1. And then we just do what we can to simplify this. So x is equal to a negative 4 plus or minus. A 44 is not a perfect square, but it is divisible by a perfect square, so we're going to go ahead and factor. We're going to do root 4 times root 11 all over 2. So x is a negative 4 plus or minus, the square root of 4 is 2, so we get 2 radical 11 all over 2. This ratio can actually be reduced. A couple of approaches to doing this. You can use factoring and canceling, kind of like we did over here. Or you can separate the fractions. Typically, I don't like using that method, but in this one it's very convenient. So this will be a negative 4 over 2 plus or minus 2 root 11 over 2. And now it's very clear that things reduce here. So we get a negative 2 plus or minus the square root of 11. So those are our 2 roots. Now on this example, since we have irrational roots, rather than writing this as a list, I'm going to do the approximations for both the roots. So one of the roots is x is equal to a negative 2 minus root 11. And we'll go ahead and just approximate that with a calculator. So when you calculate this, you're going to follow the order of operations. You're going to take the square root of 11 first. And so in my calculator, that ended up being about 3.316. It's a irrational number. The square root of any prime, remember, is an irrational number. And if you're using your calculator altogether, we have to make that negative, so have that minus sign in front of the radical. Ignore that dot, that was a mistake. But anyway, we have the negative 2, so we're going to just subtract the 2. It's like adding negative 2. And so one of the roots to the equation ends up being a negative 5 and 317 thousandths. I went ahead and rounded to the thousandths place. I don't really have any precedence for rounding here in this example, so I just decided to round to the thousandths. The other root is going to be x is equal to a negative 2 plus root 11, and we can go ahead and approximate that as well. Now that one's going to end up being positive. So you will start with the square root of 11. We're following the order of operations here. The square root symbol is also an exponent. So we'll take the square root of 11, you get that 3.317 roughly, and then we'll subtract out the 2, which is like adding a negative 2. And the other root then is 1 and 317 thousandths, roughly. So there's our two approximations to the roots. You know, the exact roots are over here, a negative 2 plus or minus root 11. But here's our approximations. And sometimes the approximations are very practical, especially in physics. So sometimes on certain problems, some of the more complicated ones in physics, you might have to break out the quadratic formula. But I did mention in the video on the square root property, a lot of problems in physics involve using the square root property. So you'll probably use that more frequently in physics. But every once in a while for complicated problems, you might need to use the quadratic formula. So the quadratic formula is very powerful. It is the most powerful approach to solving quadratic equations. So very useful formula. Definitely you want to memorize the discriminant and take that approach because it kind of streamlines your thinking and keeps it very organized. So we highly recommend that you always start with the discriminant when you're using the quadratic formula. So we will follow up this video with a video that has a bunch of application problems involving quadratic equations. Some maybe that we can use the square root property on, and then maybe some with the quadratic formula. Thanks for watching, and make sure that you do follow up on the next video.